Welcome to today's lecture on basic fundamentals of DC machines. In the previous lectures, we have already discussed the basic concepts such as electromagnetic induction and magnetic fields behind the working of electrical machines. Also, we have discussed the construction, working principle, EMF generation, torque production and the various types of machines based on excitation including generators and motors. In today's lecture, we will explore the performance characteristics of DC machines covering the characteristics of DC generators, characteristics of DC motors, control of DC machines and their applications. Understanding the DC machine performance characteristics is essential to know how they work and how to use them in different applications. Usually these consist of voltage current characteristics, speed torque characteristics, speed current characteristics, efficiency, load characteristics, field characteristics, performance under different conditions, temperature effects, brush and commutator wear and regenerative braking characteristics. Understanding these characteristics helps in selecting the appropriate DC machine for a specific application which ensures optimal performance and extends the lifespan of the machine. The voltage current characteristics. When we say voltage, we have no load voltage and full load voltage. The no load voltage is the voltage when the machine is running without any load. The voltage generator or applied is at that situation is no load voltage. Full load voltage is the voltage under full load conditions and this can be different from no load voltage due to voltage drops in internal resistances. Next is speed torque characteristics. Speed versus torque curve shows how the speed of DC motor varies with the load torque. For a DC motor, the speed increases as torque increases and the relationship is generally non-linear in nature. Next comes the speed current characteristics. Speed versus armature current shows the speed of DC motor is changing as the armature current changes. Next is efficiency. The mechanical efficiency is the ratio of mechanical power output to electrical power output, typically expressed as a percentage, whereas the overall efficiency takes into account the losses in the stator, rotor and friction. Next is our load characteristics. Here we have load curve and load regulation. Load curve illustrates the relationship between the applied load to the motor and its speed, whereas load regulation is a measure of how well the DC machine maintains its output voltage or speed when there is variation in load. Next characteristic is the field characteristics. So when we talk of field characteristics, we have field current versus voltage characteristic and field strength versus speed characteristic. Field current versus voltage shows how the voltage across the machine varies for a given field current, whereas field strength versus speed characteristic shows the strength of the magnetic field produced by the field winding and how it affects the speed and torque characteristics of the machine. Now, the performance under different conditions mainly consists of starting characteristics and the overload characteristics. The starting characteristics means how the machine performs during startup, including the starting torque and current. The overload characteristic shows how the machine handles temporary overload conditions without significant performance degradation or damage. Next is temperature effects. When the machine is in operation, there is an increase in temperature which affects the performance and can lead to overheating if the temperature rise is not properly managed. Then comes our brush and commutator wear. The wear characteristic shows the rate at which brushes and commutators wear out, which affects the maintenance and the longevity of the machine. The last one is our regenerative braking characteristics. The regenerative braking performance shows the efficiency and effectiveness when the DC machine operates as a generator to recover energy during braking. Now, let us see the characteristics of DC generators in detail. The characteristic of DC generators describe how they behave under various operating conditions. The first operating condition is the no load characteristic or open circuit characteristic, abbreviated as OCC, or also it is known as magnetization characteristic. This characteristic is plotted between the generated no load voltage E0 and field current IF. So, E0 is the voltage generated by the DC generator when no load is connected to it and reflects the open circuit voltage. Here the speed of the generator is maintained constant while plotting the characteristic. We know for a generator E is equal to Pn phi z upon 60A, where Pnz upon 60A is equal to constant. So, we can write E as proportional to phi, or we can also write down E proportional to IF when phi is proportional to IF. So, the flux, if proportional to the field current IF, means the induced EMF increases directly as the field current IF increases. But after certain value of field current, the core gets saturated. This is due to saturation effect. What is saturation effect? Even though there is an increase in the field current, the flux remains constant. This phenomena is known as saturation. Hence, the voltage also remains constant. Thus, the characteristic is linear till saturation and it bends after that, which is shown in the characteristic, and the voltage also remains constant though the field current keeps on increasing. So, if the magnetization characteristics for various speeds are plotted, we will get the characteristics as shown for N1, N2, N3. For lower speeds, the generated voltages are less, so characteristics for lower speeds are below the characteristics for high speeds, as can be seen from the magnetization characteristics plotted for speeds N1, N2, N3. Second one is the load characteristics or load voltage characteristics. Load characteristics represents how the terminal voltage Vt of the DC generator varies with the load current IL. It shows a drop in voltage as the load current increases due to the internal resistance of the generator and the voltage drop in the armature windings. The characteristic curve usually starts high when the generator is unloaded and decreases with increasing load, as you can see from the characteristics. Now, the load characteristics are of two types, that is internal characteristics and external characteristics. Characteristics of separately excited DC generator. Let us see one by one for separately excited DC generator, then shunt, then series. Now, the no load characteristic for the separately excited DC generator is obtained by the circuit diagram which is shown. The rheostat acts as a potential divider and it is used to control the field current and the flux. As the field current IF is changed, the induced EMF E0 also changes, which is measured on the voltmeter connected across the armature. As IF increases, flux phi increases and E0 increases after point B. As you can see, saturation occurs, so the phi becomes constant and hence E0 saturates. Next is the load characteristics or load voltage characteristics. When the generator is loaded, the armature current IF flows and armature reaction comes into picture. Due to this, terminal voltage Vt becomes less than the no load rated voltage. At every load, field current is varied in such a manner that rated armature current flows into the load, so that armature current and speed are maintained constant. O to A is the amount of field current required to circulate the rated armature current when load resistance is reduced to 0, as can be seen from the characteristic. Next comes the internal and external characteristic curve. The internal characteristic curve shows the relation between the internal generated EMF E0, as we have seen, and the load current IL, taking into account the armature resistance drop. This curve shows how the internal EMF decreases with an increase in load current. External characteristic curve is the relationship between the terminal voltage Vt and load current IL, considering the effects of armature resistance and other losses which are taking place in the machine. It is similar to the load voltage characteristic, but explicitly shows the terminal voltage as the load current changes. We plot the graphs for constant field current in both the cases. In case of separately excited DC generator, induced EMF is totally dependent on flux phi, that is field current IF. Hence, to have control over the field current, in case of separately excited DC generators, field regulator is necessary. We should know about a self-excited DC generator, that is the conditions for voltage buildup of a self-excited generator. In self-excited machine, there is no external source for providing the excitation current. So, there must be some residual magnetism in generator poles. Due to retentivity property of all the magnetic materials, they possess some amount of flux which is known as residual magnetism, and this is say approximately 5 to 10% of the rated value. The connection of the field winding should be such that the field current strengthens the residual magnetism. If the field terminals are wrongly connected, then separate the field terminals and excite with a low voltage for some time to re-establish the residual magnetism. This process is called field flashing. The resistance of the field current should be less than the critical resistance, where the critical resistance is denoted by RC and is the total field resistance above which the generator fails to build up its voltage. The last condition is that when the generator builds up voltage under load condition, the load resistance must be more than the critical load resistance. Now, let us see the characteristics of DC shunt generator. Shunt generators are most commonly employed as there is no need of separate excitation. The first one is no load characteristics. These characteristics are obtained by removing the field winding and operating the generator as a separately excited generator. No load characteristics of both the separately excited and shunt generators are same. So, next is our load characteristics. The load characteristics can be obtained in a similar manner as separately excited generator, but only difference is in their armature currents. For shunt generator, armature current is given by sum of load current and shunt field current, whereas for separately excited generator, armature current is same as load current. These characteristics are similar to separately excited generator. The internal characteristic curve for DC shunt generator, let us see how it is plotted. The internal characteristic is plotted as E versus IL, that is EMF and load current. Ideally, the induced EMF is not dependent on the load current or armature current IA, but as the load current increases, the armature current increases to supply the load demand. As armature current increases, armature flux increases. This effect produced by armature flux on the main flux produced by the field winding is called armature reaction, and due to this armature reaction, main flux pattern gets distorted. Hence, lesser flux gets linked with the armature. Thus, the generated EMF drops due to armature reaction. This is shown in the curve. Next is our external characteristics curve. We know that for a DC shunt generator, E is equal to Vt plus Ia Ra. Here we are neglecting the other drops. So, as the load current IL increases, the armature current Ia increases, and Ia Ra, the drop also increases. The terminal voltage Vt equals to E minus Ia Ra decreases as a result. But the value of armature resistance is very small. So, the drop in terminal voltage as IL changes from no load to full load is very small. Hence, the DC shunt generator is called as constant voltage generator, and the characteristics is drooping in nature as shown. Let us now come to the characteristics of DC series generator. These generators are mainly used as series boosters connected in line to neutralize the effect of line ohmic drop. The first one is no load characteristics. In series generator, the armature winding current and the field current are same. So, no load characteristics cannot be obtained. If we want to draw the no load characteristics, it should be run as a separately excited generator. The load characteristics, that is the internal and external characteristics, can also be only obtained by running machine as a separately excited machine. In case of series generator, Ia is equal to Isc is equal to IL, that is armature current is same as series field winding current is same as load current. Since the phi flux is directly proportional to the current Isc, as the load current increases, flux also increases, and the induced EMF E is proportional to flux, hence induced EMF also increases. Thus, the characteristics of E against I, that is internal characteristic, is of increasing nature. As the armature current Ia keeps on increasing, armature reaction increases, but its effect is negligible compared to increase in E. But it is to be noted that for high load current, saturation occurs and flux remains constant. In such a case, due to armature reaction, E starts decreasing as shown by the dotted line in the characteristics. As IL is equal to Isc keeps on increasing, the drop Ia into Ra plus Rac also keeps on increasing. Thus, the external characteristics is also of rising nature as E increases, but it will be below the internal characteristic due to the drop Ia into Ra plus Rc. In self-excited series generator, open circuit characteristics cannot be obtained. In open circuit condition, Isc is equal to IL is equal to 0. Hence, induced EMF is also 0. Thus, open characteristics is possible only by separately exciting the field winding. In practice, when there is no load, that is the load current IL is equal to 0, then there exists certain induced EMF due to residual flux retained by the field winding. Hence, for zero load current, there is a voltage present and the internal and external characteristics do not pass through the origin as shown. Now, let us see the characteristics of the compound generator. The no load characteristics of a long shunt or short shunt compound generator is same as the shunt generator. The external characteristics depend on whether the generator is cumulatively compounded or differentially compounded generator. For a cumulatively compounded generator, the total flux is given as a sum of shunt field winding flux and the series field winding flux. In this configuration, the series field winding contributes to the main field flux in the same direction as a shunt winding. This additive effect enhances the total magnetic flux. As the load current increases, the series winding contribution to the magnetic flux also increases. Thus, induced EMF increases and the terminal voltage also increases. But as the armature current IA increases, the various voltage drops and armature reaction drop also comes into picture. Hence, there is drop in the terminal voltage. If the drop in terminal voltage Vt is more dominating than the increase in Vt due to increase in flux, then the generator is called undercompounded and its characteristics is drooping in nature. Whereas if the drop in terminal voltage Vt due to armature reaction and other drops is much less than the increase in Vt due to increase in flux, then generator is called overcompounded and its characteristics is rising in nature. If the effects of two are such that on full load current, Vt is same as no load induced EMF, that is, effects are neutralizing each other, then the generator is called flat compounded or level compounded. Differentially compounded generator. The net flux here is the difference between the shunt field winding flux and the series field winding flux. As the load current IL increases, ISH is almost constant, but the total flux decreases rapidly. Hence, the resultant flux reduces. So, the induced EMF E and the terminal voltage also decreases drastically. There is drop due to armature resistance, series field resistance, armature reaction, due to which the terminal voltage drops further. Thus, we get the characteristics of such differentially compound generator as shown. Now, let us see what is speed regulation. Speed regulation measures how the speed of the generator changes with the changing load conditions. The regulation characteristic shows the percentage change in speed from no load to full load. We can say that speed regulation is given by the speed at no load minus the speed at full load divided by the speed at full load into 100. The DC generators usually exhibit a drop in speed with an increase in load. Next comes the voltage regulation. Voltage regulation is the ability of the generator to maintain a constant voltage output despite the variations in load. It is a measure of how the terminal voltage of the generator changes from no load to full load conditions and expressed as percentage change in voltage from no load to full load. The good voltage regulation indicates that the generator can maintain a steady output voltage even when there is a variation in load. Efficiency. It is the ratio of electrical power output to mechanical power input, reflecting how effectively the generator converts mechanical energy into electrical energy. And efficiency is affected by factors like losses in the armature windings, field windings and friction. Now let us see the characteristics of DC motors. The nature of these characteristics can easily be obtained by using speed and torque equations. There are three characteristics basically. The torque current characteristics plotted between torque and armature current. They describe the relationship between the torque produced by the motor and the armature current and are also known as electrical characteristics. The second one is speed current characteristics, that is N versus Ia, shows the speed of the motor with the variations in the armature current and shows that for a constant field current the speed increases as the armature current increases, though this relationship is affected by the load conditions. The third one is the speed torque characteristic N versus T, showing the relationship between the speed of the motor and the torque it produces. These are also called mechanical characteristics. Typically for a DC motor, the speed decreases as the load torque increases. Characteristics of DC shunt motor. The first one is torque current characteristic T versus Ia. For a DC motor, the torque is proportional to the product of flux and current, armature current. For constant values of Ra and supply voltage Vt, Ia is also constant and hence the flux is also constant. So, we can write down that torque is proportional to Ia. The equation represents a straight line passing through the origin, as you can see in the characteristics plot. The torque increases linearly with the armature current. It is seen that armature current is decided by the load. So, as the load increases, armature current increases, increasing the torque developed linearly. Now, if the shaft torque is plotted against the armature current, shaft torque being less than the armature torque and the difference between the two is a loss torque Tf, then on no load the shaft torque TSH is equal to 0, but armature torque Ta is present, which is just enough to overcome the stray losses shown as Ta naught. The current required is Ia naught on no load to produce Ta naught, and hence TSH Ta naught line has an intercept Ia naught on the current axis. Characteristics of DC shunt motor. Speed current characteristics of DC shunt motor, that is N versus Ia. From the speed equation, we know that speed is proportional to Eb by phi, where Eb is our back EMF and phi is the flux. Eb can be written as V minus IaRa by phi. When phi is constant, N becomes proportional to V minus IaRa. So, as load increases, the armature current Ia increases and hence drop IaRa also increases. Hence, for constant supply voltage, V minus IaRa decreases and hence the speed also decreases. But Ra is very small. For change in Ia from no load to full load, drop IaRa is very small and hence drop in speed is also not significant from no load to full load. So, the characteristic is slightly drooping in nature as shown. But for all practical purposes, these type of motor are considered to be constant speed motors. The speed torque characteristic as shown illustrates the relationship between motor speed and torque. They can be derived from the above two characteristics. The graph is similar to the speed armature current characteristic, as torque is proportional to the armature current. The curve shows that the speed almost remains constant, though torque changes from no load to full load condition. Let us now see the characteristic of DC series motor. The first one is torque current characteristic plotted between torque and armature current. In case of series motor, the series field winding carries the entire armature current. So, flux produces proportional to armature current, that is phi is proportional to Ia. Hence, torque, which is proportional to product of flux and current, is given as the square of the armature current. Thus, we can say that this relation is parabolic in nature, as you can see from the characteristic. As load increases, armature current increases, hence torque produced increases, which is proportional to square of armature current up to a certain limit. As the entire armature current passes through the series field, saturation of electromagnet may occur. That is, even when the current through the winding increases, the flux produced remains constant. So, after saturation, the characteristic takes the shape of a straight line as flux becomes constant. The difference between the armature torque and the shaft torque is the loss torque, which is also shown in the characteristic. So, at start, the armature torque is proportional to the square of armature current. So, the motors can produce high torque for small amount of armature current. Hence, the DC series motors are suitable for the applications which demand high starting torque. Next is the speed current characteristics of DC series motor plotted between the speed and the armature current. As we have seen in the speed equation in the previous slide, our speed is proportional to the back EMF divided by the flux given by V minus IaRa divided by phi. So, when phi is proportional to the armature current Ia, speed is given as Vt minus IaRa minus Isc Rsc divided by Ia. So the values of the armature resistance and the series field winding resistance are so small that the effect of change in speed overrides the effect of change in drop on the speed. Hence, in the speed equation, Eb is equal to Vt, which can be assumed constant. So the speed equation reduces to N is proportional to 1 by Ia. So the speed armature current characteristic is a rectangular hyperbola type as shown. The speed armature current curve is typically downward sloping. The curve demonstrates that the speed of the motor drops as the load and consequently the armature current increases. Third one is our speed torque characteristic, which is showing the relationship between the speed and the torque of the motor. In case of series motor, the torque is proportional to the product of flux and armature current, but flux phi is equal to Ia. So torque becomes proportional to the square of current and N is proportional to 1 by Ia. So N is proportional to 1 by root over Ta. The speed of DC series motor is very low at high torque levels. This is because the motor speed decreases as the load increases and more torque is required to drive the increased load. Whereas the motor speed is high at low torque levels. The motor runs faster when there is little resistance or load. The speed torque characteristic curve for a DC series motor is typically a steep downward sloping curve. On no load condition, the torque is very less and hence the speed increases to a dangerously high value. So we should not operate this motor on low load conditions. Next comes the characteristics of DC compound motor. Compound motor characteristics basically depends on the fact whether the motor is cumulatively compounded or differentially compounded. All the characteristics of compound motor are the combination of shunt and series characteristics. In cumulatively compound motor, the shunt field winding produces a definite flux and series flux helps the shunt field flux to increase the total flux level. Whereas in differentially compounded motor, as the two fluxes oppose each other, the resultant flux decreases as the load increases. The various characteristics of both the types of compound motors, cumulative and differential, are shown. Starting characteristics. The starting characteristics of a DC motor are important for understanding how the motor performs when it is initially turned on and how it progresses from a standstill to operating speed. These characteristics involve the examining of parameters such as starting torque, starting current and the behavior of the motor as it accelerates. Starting torque is the torque produced by the DC motor when it starts from rest and overcomes inertia and start the rotation of the motor. The DC motors, particularly series wound motors, are known for their high starting torque. This is due to the fact that in series motor, the field winding and the armature winding in series, which means the field current is equal to the armature current. At startup, the armature current is high because the back EMF is 0, leading to high torque. If we see the starting current, it is the current drawn by the motor when it is first started. So we need to have the DC motor starters and we need to see that what is the necessity of DC motor starters. At startup, the armature is stationary, so the back EMF is 0. This causes the starting current to be very high, potentially several times higher than the normal operating current. The starting current is mainly limited by the armature resistance. If the motor is directly switched on to the mains, the armature will draw a very heavy current as Ia is equal to V upon Ra because of the small armature resistance which may cause a very severe damage. To avoid this, a suitable DC motor starter must be used. 3-point and 4-point starters are used for DC shunt and compound motors, and 2-point starters are used for DC series motors. The regulation characteristics measure how well the motor maintains its speed with varying load conditions. The DC motors with good regulation characteristics will maintain a relatively constant speed even with a large variation in load. Now, after studying the characteristics of DC generators and DC motors, let us see the control of the machines. The DC machine control is a very important process of operating the machine to attain specific performance characteristics like torque, speed and direction. There are several methods and strategies for controlling DC machines, and each of them are suitable for different applications and requirements. Let us see an overview of the main control methods which will be applicable for the coming lectures based on for drives. The first one is speed control. The speed control can be attained by armature voltage control, field current control, and both armature voltage and field current control. The second one is torque control. The torque can be controlled by again the armature current control and field current control. The third one is direction control. The direction can be controlled by reversing the armature connections as well as field connections. The next is dynamic braking and regenerative braking. And the last one is your feedback control system, which can be implemented by using speed feedback control as well as torque feedback control. The speed control method, the first speed control method, that is the armature voltage control, is used to control the speed of DC motor by varying the voltage supplied to motor's armature. And we use this technique widely because of its simplicity and effectiveness in achieving a wide range of speeds. The speed N of DC motor is determined by the voltage applied to the armature and the magnetic flux produced by the field windings. The relationship between the speed and the armature voltage VA has been expressed as N proportional to EB by phi, which we have seen earlier, given by Vt minus IaRa by phi. So, increasing the armature voltage increases the speed, while decreasing it reduces the speed. This method can be achieved by using a variable resistor or rheostat or electronic speed controller such as pulse width modulation controllers. This can be achieved by using a variable resistor, rheostat or electronic speed controllers such as pulse width modulation controllers. And this method is common in applications requiring variable speed control and where speed regulation is must. Next is field current control. The speed of DC motor can also be controlled by varying the field current, that is the current flowing through the field winding. Decreasing the field current decreases the magnetic flux, leading to increase in speed. Since the magnetic flux phi is proportional to the field current IF, varying the field current changes the flux. By adjusting this, the motor speed can be adjusted. This can be achieved by using a variable resistor in series with the field winding or electronic controllers, and this method is often used in conjunction with armature voltage control for more precise speed regulation. The third one is the combination of both armature voltage and field current control, and it provides a fine control over the motor speed and torque characteristics. By adjusting both the parameters, it is possible to achieve a wide range of speeds and responds to varying load conditions. So, it finds its application requiring precise and adjustable speed control. The second method is by controlling the torque. For controlling the torque, we use armature current control method. Here, the torque of the DC motor is proportional to the armature current. So, controlling the armature current directly affects the torque output, as we have just seen that in DC series motor, the magnetic flux phi is proportional to armature current Ia. So, the torque can be described as T proportional to Ia square. This can be done using current controllers or feedback systems to adjust the armature current to desired level, and are essential in applications where torque needs to be precisely controlled, such as in robotics and conveyor systems. The second method is the field control method. By varying the field current affects the torque speed characteristics of the motor. Reducing the field current lowers the magnetic flux and can increase the torque at a given speed, as in DC motor the magnetic flux phi produced by the field winding is proportional to the field current IF. This can be achieved by using adjustable field resistors or electronic field controllers, and are used to adjust torque characteristics in conjunction with speed control methods. The third one is directional control. We can achieve the direction control by reversing the armature connections. The direction of rotation of DC motor is determined by the direction of current flow through the armature windings. Reversing the direction of current flow through the armature windings changes the direction of magnetic field produced by the armature. This reversal of the magnetic field direction causes the motor to rotate in the opposite direction. This is done by using a switch or a relay to change the polarity of the armature connections. This is the most simple and effective method for applications requiring bidirectional operation, such as in electric vehicles and conveyors. We can also reverse the field connections, and by this method we change the direction of rotation of DC motor, and this can be achieved by using a switch or a relay to reverse the connections to the field windings. They are less common than armature reversal, but can be used in some specific applications. Next is dynamic braking and regenerative braking. Dynamic braking is a technique used to stop or slow down a DC motor by using the motor itself as a brake. Dynamic braking involves converting the kinetic energy of the motor's rotation into electrical energy, which is then dissipated as a heat. This is achieved by utilizing the motor's own armature windings as a generator. A braking resistor is connected across the armature windings to dissipate energy, and this finds its application in requiring quick stopping of the motor, such as elevators and some conveyor systems. Regenerative braking. The motor operates as a generator here during braking, converting kinetic energy back into electrical energy and feeding it back to the power supply. Last is our feedback control system. Here the speed feedback control system uses sensors to monitor the actual speed of the motor and adjusts the control inputs to maintain the desired speed. It employs devices such as tachometers or encoders to provide feedback, which is processed by a controller, and applications are places where precise speed control is required, such as robotics and automated manufacturing. In torque feedback control, it monitors the actual torque output and adjusts control inputs to achieve the desired torque. It uses torque sensors and feedback mechanisms to regulate current and field strength. This method is useful in applications which require accurate torque control, such as high precision machines. So, in today's lecture we have discussed the performance characteristics of the DC generators, DC motors, and we have seen the applications as well as different types of controls of DC machines which will be utilized in their application as drives. Thank you. Thank you very much.